All right, this is a little short topic video on the concept of oxidation and reduction reactions. So we didn't cover this a ton in class, so I wanted to make a little short video just to go over the basic concepts again. So remember, we're talking about oxidation or reduction. You can alternatively call them reduction oxidation reactions, which is traditionally where the kind of abbreviation comes from. They're typically referred to in shorthand as redox reactions. In the very simplest terms, what we're talking about is the movement of electrons between components in a system, in a chemical system. Just like with conservation of mass, you cannot gain or lose electrons out of the chemical system that you've gotten built in your chemical reaction. So the only thing you can do is move electrons from one location to another. Now, typically, we're talking about how bonds form, but in this case, we're talking about physically moving electrons from one component of the system to another component of the system. Now, in simplest terms, we can kind of come up with a mnemonic for how we describe the movement of electrons. The mnemonic that most people use, and a mnemonic is a kind of auditory clue that hints at what a piece of information we're trying to remember. I know those of you who've taken A and P, you learn a lot of mnemonics in A and P. We don't use a ton of them in chemistry or in micro, but I know a few like Reggie-Biv and taxonomic ranks in biology. But one I do know in chemistry is called oil rig. Now, oil rig is a way to describe the flow of electrons in a redox reaction. So what oil rig stands for is oxidation is loss of electrons, reduction is gain of electrons. Now, this is a simplification of the system. There are redox systems that are a little more complicated than this, but it's a really good first step at how to look at them. So again, oil rig. Oxidation is loss, reduction is gain. So the best way to look at this is to look at an example, right? Redox reactions can be divided into what are called half reactions. In other words, they can be split apart into multiple pieces. And what we're looking at is we're looking at electronically what happens to each part of the system. So let's get and look at this system here. So we have a simple combination reaction. Solid sodium metal exposed to chlorine gas produces table salt, sodium chloride. Granted, probably one of the most toxic ways to create table salt, but that's beside the point. Simple combination reaction. But when we dig down and we drill down into the system, there's some really interesting chemistry going on. Because the reactants in this reaction, the sodium metal and the chlorine gas, these are both electrically neutral, right? Sodium metal is not the same as sodium ions. Sodium metal is electrically neutral. It has one electron in its outer shell, matches up to the number of protons it has, so no electric charge. Chlorine gas, diatomic chlorine, is electrically neutral. It's two chlorine atoms covalently bound by a single bond. All right. So in both these cases, we have electrically neutral species. Now, when we move to the other side, we move to the product side of the system. Here, we have an ionic species because we got sodium chloride. Now, in this case, both the components have an electric charge to them. Sodium metal becomes sodium ion, which is a positive one charge. Chlorine gas gets converted to chloride ion, which is a negative one charge. So we can separate these two reactions out. We can talk about them individually. We can talk about how sodium metal becomes sodium ion and how chlorine becomes chloride. In each of these cases, there is a loss or gain of electrons. So in the case of the sodium has to go from a zero charge to a +1 charge. And just like a mathematical equation, if we consider that arrow to be like an equal sign, the charges on both sides of that, the left and the right side of that, have to equal out to each other. So since sodium on the left equals 0 and sodium ion on the right equals 2 plus, I need 2 electrons on the right also to cancel out the 2 plus to get me back to 0. And with the chlorine, I go from a 0 state on the left to a -2 state on the right, which means on the left side, I need 2 electrons to balance out the charges. So we can see by looking at these half reactions that the sodium is losing electrons. Because when we go to the product side, it's become sodium ion plus these 2 electrons is thrown off. So it's lost 2 electrons, so therefore the sodium is oxidized. The chlorine, on the other hand, has to pull 2 electrons in to become chloride. So the chlorine is reduced. Now here's another example of a half reaction. So we'll look at this one, we'll walk through this. So again, here we've got a fairly simple system. Instead of a combination reaction, we're looking at a decomposition reaction. Okay, so decomposition, we're looking at silver bromide. Silver bromide is broken down to silver metal and bromine gas. This can happen under extreme heat. All right. Same thing happens with cinnabar, which is a type of mercury oxide. You can break down mercury oxide to mercury metal with extreme heat. So the silver bromide breaks down into silver metal and bromine. So let's take this apart. Let's look at the components, the 2 what we call half reactions. So in this case, the half reactions are going to involve silver and bromine. So on the reactant side, I have silver ion, because it's part of an ionic compound, silver bromide, silver ion becoming neutral silver metal. And the other component, I have bromide, the ionized form of bromine, becoming bromine. All right. So in each of these cases, I'm going from an electrically charged state to a neutral state. Now, in silver's case, I have 2 + 1 charges on the left and a 0 charge on the right. So I need to add 2 negative charges into that system to balance out the left side with the right side. On the bromide's case, I have 2 negative charges on the left and no charge on the right. So I have to add 2 negative charges into the right to balance out the left and the right side. So when I look at these two, now when I look at silver, right? Last time we talked about how the metal was oxidized, but here we're doing the exact opposite. In the last case, we went from a neutral metal to a positively charged ion. Here we're going from a positively charged ion to a neutral metal. So we have to actually add electrons in, right? So I'm no longer losing electrons in the metal, I'm gaining electrons back into the metal because the positively charged ion needs electrons to become neutral. So in this case, I am reducing the silver. I'm reducing silver ion to silver metal. And I am oxidizing bromide back to bromine. Okay? So these are fairly straightforward examples of half reactions. I don't expect you to be able to draw really good half reactions or write really good half reactions yet, but I want you to be able to recognize what reduction and oxidation mean, right? So when we talk about gain and loss of electrons, you should be able to understand what that means. Now, another thing we see a lot in redox are what are called spectator ions. Spectator ions are a system in which not everything participates, right? This is very common in single replacement reactions. Those metal exchange reactions or anion exchange reactions we talked about. So here's a great example. If I expose bromine gas to sodium chloride, the bromine will displace the chlorine and you'll get chlorine gas and sodium bromide, right? So this is a traditional single replacement reaction. It's also a redox reaction. We could talk about how chlorine and bromine change states. So the chlorine, just like before, and I took the state functions out for clarity, the chlorine, as before, goes from chloride to chlorine, so it needs to get rid of 2 electrons. The bromine goes from bromine to bromide, so it has to gain 2 electrons. So those are oxidized and reduced. But what about sodium? On the left side of the equation, the sodium is +1 ion. On the right side of the equation, the sodium is +1 ion. The sodium hasn't undergone any change in the system. So just like a spectator in the stands isn't actively participating in the game, the sodium is in the system, but it's not actively participating in the chemistry that's occurring. it doesn't change in any way, shape, or form, chemically speaking, during the reaction. So we refer to the sodium ion as a spectator ion. All right. So whenever you're writing redox reactions, you kind of ignore the spectator ions because they're not part of the chemistry that's actually occurring. What you're really interested in is how the electrons are moving in the system. Now, the last thing I wanted to kind of put as a caveat in here, don't dig too deep into the book's explanation of redox reactions. The book goes a lot deeper than we're going to go, okay? Once you start hitting the part in the book where it starts talking about oxidation number, you can kind of, okay, I don't need to read from there on out. Oxidation number is a much broader definition of the redox system. It's more applicable to more systems. What we've talked about is pretty much only applicable to direct ionic exchanges. We can expand redox into a more broad definition that's very useful in like organic chemistry and biochemistry, but that's beyond the scale of where we're going to be. So don't go digging deep into the weeds once you get to where it says oxidation number. Okay? So hopefully this has helped clarify a little bit about redox systems for you guys.